When you watch an aerobatic stunt plane flip completely upside down and continue flying in a perfectly straight line, it seems to break the fundamental rules of physics. For decades, textbooks have taught us that planes fly solely because of the special, asymmetric, curved shape of their wings. But if that were true, an upside-down plane, or a plane with totally flat wings like the Wright brothers used, would simply plummet to the Earth. So where did those textbooks go wrong? And how do planes actually fly? Though we don't always think of it this way, air is a fluid medium. As an object moves through it, the fluid exerts a force on the object. This force is split into two components: drag, which pushes back against the object, largely due to frictional wall shear stresses, and lift, the upward force required to overcome gravity and stay aloft. For modern planes, lift is mostly generated by streamlined structures called airfoils, better known as wings. For a long time, the most pervasive and false description of lift has been the longer path or equal transit time explanation. It states that because a wing is curved on top and relatively flat on the bottom, air molecules traveling over the top cover a longer distance. To reach the wing's trailing edge at the exact same instance as the air that went below, the air on top must travel faster. According to Bernoulli's principle, faster flowing air exerts less pressure, thereby creating a pocket of lower pressure that lifts the plane. Job done, right? Nope. This explanation has been thoroughly debunked. Experiments show that airstreams splitting at the front of the wing don't need to meet back up. In reality, the air traveling over the top goes significantly faster, reaching the trailing edge long before the air beneath it. To get a sense of how lift is actually created, we have to look at how a wing affects the movement of the air around it. As fluid flows past the airfoil, it hits a spot near the leading edge called the stagnation point, where the fluid's velocity is reduced to zero. Here, the air splits. Due to a complex aerodynamic concept known as circulation, the air traveling over the top of the wing accelerates. Just as the old explanation suggested, Bernoulli's principle dictates that this increase in velocity creates an area of low pressure above the wing, while the slower moving air below creates high pressure. Adding up this pressure difference across the wing gives us our upward lift. But remember our upside-down stunt plane? A symmetrical wing doesn't have that classic curved shape known as camber. If pressure differences from wing shape were the only way to generate lift, upside-down flight would be impossible. This brings us to the other vital half of the equation, Newton's third law of motion. A wing doesn't just slice through the air, it deflects it. The angle between the wing and the oncoming air is called the angle of attack. As a plane pitches its nose up, the air hitting the underside of the wing is forcefully deflected downward. Meanwhile, thanks to the Coanda effect, the fast-moving air traveling over the top surface is guided along the wing's contour and swept downwards as well. This creates a massive displacement of air called downwash. And as Newton's third law tells us, for every action there is an equal and opposite reaction. By forcefully pushing the air down and back, the air pushes the wing up and forward. This is exactly how a perfectly flat wing or an upside-down stunt plane with symmetrical airfoils manages to fly. By simply increasing their angle of attack, they force air downwards, generating the lift they need. While increasing the angle of attack or adding camber deflects more fluid and increases lift, there are limits. If a wing is deeply angled too far, usually past a critical value of about 16 degrees, it can be disastrous. The fast-moving boundary layer of air on top of the wing is no longer able to remain attached to the surface. It violently detaches, creating a turbulent wake. This destroys the pressure distribution and drastically reduces lift while skyrocketing drag. This sudden loss of flight capability is called stalling, and it is incredibly dangerous. To safely manage lift without stalling, modern aircraft are equipped with mechanically adjustable flaps and slats. During takeoff, when a plane is flying slowly, flaps are extended to increase the wing's camber, generating massive amounts of lift. But because more lift means more drag, these flaps are neatly retracted during high-speed cruising to maximize fuel efficiency. For generations, engineers and physicists have held lengthy debates over lift. Are planes pushed up by Newton's laws of downward deflection, or are they sucked into the sky by Bernoulli's pressure differences? The truth is, neither explanation is wrong, and neither is complete on its own. There isn't a strict cause and effect relationship between the fluid's velocity, the pressure distribution, and the downturning of the air. In reality, all of these phenomena are happening simultaneously and mutually interacting. They are simply two different ways of looking at the exact same physical event. When things get too complicated, engineers rely on a set of formulas called the Navier-Stokes equations to perfectly model the airflow. Lift may retain its reputation as a confounding, highly debated concept, but whether you're cruising at 30,000 feet or watching a stunt plane fly perfectly upside down, remember, it's really all just the physics of fluid in motion.